A man steps into a machine and vanishes, intent on preventing a terrible war. He succeeds, but in doing so, he erases the very future that sent him back. This is the heart of time travel, a puzzle where cause and effect twist into knots. We are about to explore 30 of the most fascinating and scientifically grounded theories that attempt to untangle these knots. By the end, you will understand the real physics behind the fantasy and see reality in a completely new light. We will wrestle with loops that have no beginning and meet versions of ourselves from other worlds. So, what does it truly mean to change the past? The most famous of all these knots is the grandfather paradox. Suppose you build a time machine and journey back to a time before your father was born. You locate your own grandfather and for whatever reason prevent him from ever meeting your grandmother. This single action creates an impossible logical loop. If your grandfather never has children, then your father is never born. If your father is never born, then you are never born. But if you were never born, you could never have traveled back in time to interfere with your grandfather in the first place. So he would meet your grandmother, your father would be born, you would be born, and then you would go back and stop him. The loop spins endlessly, a contradiction that seems to break the very rules of cause and effect. It is the ultimate question of what it means to change your own past. How can reality resolve such a conflict? Physicists and philosophers have proposed several compelling answers. One is the principle of self-consistency, which suggests that time travel is possible, but only actions that do not create a paradox are allowed. In this view, you might travel back in time, but something would always prevent you from succeeding in your goal. Your gun might jam, you might have a sudden change of heart, or a simple accident might intervene. The timeline protects itself, ensuring that events unfold exactly as they already have, even with time travelers present. Another, more popular solution comes from the idea of branching timelines or parallel universes. In this scenario, when you change the past, you do not alter your own history. Instead, you create a new, separate branch of reality. In one universe, your grandfather died young and you never existed. But in the original universe you left, your grandfather lived, your father was born, and you still exist to make the journey. This means you could not erase yourself, only create a new world where a version of you never comes to be. The grandfather paradox is not just a quirky thought experiment. It forces us to ask what time really is. Is it a single, unchangeable thread, or a vast, branching tree of possibilities? Every theory of time travel must first find a way to untangle this fundamental knot. If the grandfather paradox presents a problem, the Novikov self-consistency principle offers a startling solution. Proposed by Russian physicist Igor Novikov, this idea asserts that the laws of physics simply will not allow a paradox to happen. Think of time not as a line you can scribble on, but as a completed, self-correcting loop. Any action a time traveler takes in the past was always a part of history. You might believe you are going back to change an event, but your presence and everything you do there were already factored into the outcome that led you to travel in the first place. It is a cosmic guarantee against contradiction. Imagine a writer who receives a beautifully bound book from a mysterious admirer. She reads it, is inspired, and decades later, using a time machine, she goes back to deliver that very same book to her younger self. Where did the book originally come from? It has no origin. It is an object and the information within it trapped in an endless, predestined loop. The book was never created, it just always existed, moving in a circle through time. This principle suggests that within a closed time-like curve, the technical term for a path through warped space-time that returns to its starting point, your free will might be an illusion. Every choice you believe you are making as a traveler has already been made. You cannot shoot your grandfather because in the consistent version of history, you did not. Perhaps your gun jammed, or you missed, or you chose not to pull the trigger. the universe conspires through countless subtle events to ensure you play your part in the story that has already been written. This has profound implications for the nature of reality. It paints a picture of a deterministic cosmos where everything is fixed. Your journey back in time is not an escape from fate, it is the mechanism of fate itself. The Novikov principle removes the anxiety of paradox but introduces a deeper mystery. Are we all just following a script, even with a time machine in our hands? But what if the universe does not enforce a single, consistent story? There is another breathtakingly elegant solution to the paradox, one that emerges from the strange heart of quantum mechanics itself. This is the many worlds interpretation applied to time travel. In this view, reality is not a single timeline but an ever-branching tree of possibilities. Every quantum event, every choice, every random occurrence causes the universe to split. Most versions of this theory are not about time machines at all, but when you introduce one, the implications are profound. A time traveler stepping into the past does not change their own history. Instead, their arrival at that moment becomes a new quantum event, a new choice point. The instant they take an action that would create a paradox, the universe simply forks. One branch continues exactly as it always did, with the traveler perhaps failing or never arriving at all. But another, entirely new branch is created where the traveler's action succeeds. You could indeed prevent your grandfather from meeting your grandmother. But you would not vanish in a puff of logic. You would simply find yourself in a brand new, separate universe where a version of you will never be born. The original you from the original timeline remains perfectly intact. This transforms time travel from a destructive act into a creative one. Every journey becomes an act of cosmic exploration, spawning new realities with each decision. The traveler is not a vandal scribbling over a precious manuscript, but an author starting a new chapter in an infinite library of worlds. This idea solves every paradox with a simple, powerful rule. Everything that can happen does happen, just in a different branch of the multiverse. There is no need for the universe to protect itself with consistency, because no single timeline ever contains a contradiction. Each one is logically sound on its own. The cost, however, is a radical expansion of reality. It means there are branches where dinosaurs never went extinct, where empires never fell, and where every possible version of your life is being lived out in parallel. Time travel under many worlds is not about changing your past, but about leaving it forever to explore the infinite possibilities of what could have been. While many worlds offers an escape into infinite branches, the mathematics of our own universe might already contain pathways to the past. These are not science fiction devices, but real theoretical structures predicted by Einstein's theory of general relativity. They are called closed time-like curves. In our everyday experience, time is a one-way street. You can move freely in space, forward or back, left or right, but you are carried inexorably forward in time. A closed time-like curve, or CTC, is a path through the warped fabric of spacetime that loops back on itself. If you were to follow such a curve, you would journey through space and eventually return to your own past, meeting a younger version of yourself without ever needing to travel faster than light. The possibility arises from the way massive objects distort reality. Einstein showed that matter and energy tell spacetime how to curve, and that curvature tells matter how to move. Under extreme conditions, this curvature could become so severe that it twists time into a loop. One of the first to discover this mathematically was the brilliant logician Kurt Gödel. He found a solution to Einstein's equations describing a universe that is slowly rotating as a whole. In such a universe, if you traveled on a rocket ship far enough in a straight line, you would eventually return to your starting point in space, but also to a moment in your own past. Gödel's universe might not match our own, but it proved that closed time-like curves were not forbidden by the laws of physics as we understand them. A more plausible candidate for creating such a path is a specific type of black hole known as a Kerr black hole. Unlike a simple, non-rotating black hole, a Kerr black hole spins at a tremendous speed. This rotation drags the very fabric of space-time around with it, like a spoon stirring a thick fluid. Theorists like Roy Kerr found that within this violently twisted region, the equations suggest the potential for pathways that could loop back in time. The catch is that these curves, if they exist, would likely be hidden deep inside the black hole's event horizon, a point of no return from which not even light can escape. So while the math allows for the possibility, nature may have placed these temporal shortcuts in the most inaccessible places imaginable. The existence of closed time-like curves forces physicists to confront deep questions. If the universe allows for such loops, then where are all the time travelers from the future? This very question is a cornerstone of another famous argument, one that uses common sense to challenge the entire idea of backwards time travel. Theoretical shortcuts through space-time offer a more tangible path than the violent heart of a black hole. These are wormholes, often visualized as a tunnel connecting two distant points in the universe, a cosmic subway through the fabric of reality. But a simple spatial shortcut is not enough for time travel. The magic happens when we introduce a crucial ingredient from Einstein's theories, time dilation. According to relativity, time does not tick at the same rate everywhere. It slows down for an object moving at a significant fraction of light speed, and it also slows down in the presence of an intense gravitational field, like near a neutron star. To transform a wormhole into a time machine, you could take one of its two mouths or openings and subject it to one of these extreme conditions. Imagine you have a stable, traversable wormhole. You leave one mouth, mouth A, safely on Earth. You then take the other mouth, mouth B, on a journey aboard a spacecraft capable of near-light speeds. After a long voyage at relativistic velocity, you bring mouth B back to Earth. Because of time dilation, less time would have passed for the moving mouth. Let us say you left in the year 2050, traveled for 10 years from Earth's perspective, but due to the effects of high speed, only 1 year passed for mouth B. When you return and place both mouths in the same room in the year 2060, a bizarre connection exists. Walking into mouth B from the year 2060 would lead you instantly out of mouth A, but into the year 2051, because that is when mouth A was relative to mouth B's slowed time. You have traveled 9 years into the past. The wormhole has become a bridge not just through space, but through time itself. Alternatively, you could place one mouth near a super-dense object where gravity dramatically slows time. The same principle applies. A persistent time difference is frozen between the two ends. This creates a two-way street. If going through one direction sends you to the past, going the other way would send you to the future. The catch, of course, is monumental. Physicists like Kip Thorne, who rigorously explored this idea, point out that creating or stabilizing a wormhole large enough for a human would likely require forms of matter with negative energy density, something we have never observed on a macroscopic scale. Furthermore, many calculations suggest that the very act of turning such a structure into a time machine might trigger a catastrophic feedback loop of radiation that would destroy the wormhole instantly. Yet the concept remains a cornerstone of theoretical time travel, a blueprint that obeys the known laws of physics while stretching them to their absolute limit. It suggests that if the universe contains these shortcuts, they might already be threaded with time. The cosmic strings we just mentioned are not science fiction, but a real theoretical possibility born from the furnace of the Big Bang. In the first chaotic moments of the universe, as the fundamental forces of nature were settling into their current forms, physicists believe immense cracks or defects may have formed in the very structure of spacetime itself. These defects are cosmic strings, unimaginably thin filaments of pure energy, thinner than a proton but stretching across the entire cosmos. A single inch of such a string would weigh more than Mount Everest, warping the space around it with its incredible density. They are like the cracks that form in ice as it freezes, but etched across the fabric of reality. And according to the work of physicist J. Richard Gott, these relics could be the ultimate time machine engines. His theory proposes a specific, mind-bending scenario. Imagine two of these infinitely long cosmic strings, perfectly parallel to each other, flying past one another in opposite directions at a significant fraction of light speed. The spacetime around each string is already severely curved, like a deep groove. As they pass, their combined gravitational fields would twist the fabric of the universe between them into an even more complex knot. Gott's calculations showed that this specific dance could create a closed time-like curve, a loop in time, in the region of space surrounding the strings. A spacecraft could fly a careful figure-8 path around the moving strings and, upon returning to its starting point, find it has arrived before it ever left. This would not require traveling into the strings or through a black hole, but simply navigating the warped geometry they create in their wake. The concept is staggering in its implications. It suggests that the universe's own ancient infrastructure, left over from its creation, might naturally contain the circuitry for time travel. These strings would be like the grooves on a vinyl record, and a ship following the right path would be the needle, skipping back to an earlier part of the cosmic song. Of course, the practical challenges are beyond colossal. First, we have no confirmed evidence that cosmic strings even exist. Second, finding two that are perfectly aligned and moving at the required relativistic speeds is a needle in a haystack search on a galactic scale. And finally, the energy required to approach such objects and execute the precise maneuver would be astronomical. Yet, as a thought experiment, it is profoundly elegant. It tells us that if the seeds of time travel are sown anywhere, they were sown in the first seconds of everything woven into the universe's blueprint. It transforms time machines from something we might build into something we might one day discover, a natural feature of a cosmos far stranger than we ever imagined. Frank Tipler took the idea of a spinning object warping time and pushed it to a logical, if physically impossible, extreme. His theoretical construct, known as Tipler's cylinder, is exactly what it sounds like, an unimaginably long, perfectly straight cylinder made of some impossibly dense material, spinning at a significant fraction of light speed. According to the mathematics of general relativity, this would not just warp spacetime, it would twist it into a helix. This effect, called frame dragging, means the rotation of a massive object literally pulls the fabric of spacetime around with it, like a spoon spinning in a jar of honey. For a cylinder of infinite length and sufficient spin, this dragging becomes so severe that spacetime is wound into closed loops around the object. A spacecraft could orbit this cylinder in a precise spiral path and, after completing a circuit, find itself not only back at its starting point in space, but also at a moment in its own past. It is a time machine built not from portals or wormholes, but from pure, staggering rotation. The cylinder itself becomes a temporal spindle, weaving threads of causality into knots. The practical barriers, however, are absolute. Tipler's solution requires the cylinder to be not just very long, but truly infinite in length. It also demands a material dense and strong enough to hold its shape under such phenomenal rotational forces, a substance that likely does not and cannot exist in our universe. So why is this impossible object so significant? It serves as a crucial mathematical proof. Tipler showed that within the framework of Einstein's equations, a time machine does not require the exotic topology of a wormhole or the mysterious conditions of a cosmic string dance. It could, in theory, be constructed from something as conceptually simple as a spinning rod, provided you had the infinite resources of a god. This moves time travel out of the realm of purely quantum or cosmological phenomena and into the domain of engineering, however fantastical. It tells us that the potential for closed time-like curves is woven into the very geometry of rotation and mass, a fundamental property of a relativistic universe. The cylinder is a thought experiment that illuminates a profound truth. In a cosmos described by Einstein's rules, the line between the future and the past may be far more fragile than we ever believed, waiting to be coiled into a loop by the right kind of spin. While objects like books can loop through time, what about the ideas inside them? The bootstrap paradox tackles information with no beginning. Imagine a brilliant composer struggling with writer's block. One evening, a mysterious visitor arrives at her door, handing her a sheet of music for a breathtakingly beautiful symphony. She is stunned but inspired. She copies the music and spends her life performing this masterpiece, which becomes the defining work of the century. Decades later, now an old woman and a celebrated artist, she builds a time machine. She decides her younger self needs that initial spark of genius. She travels back in time, finds her own home on that fateful night, and hands the sheet music to the struggling composer she once was. The symphony is born, but here is the impossible question: who actually composed it? The music was never created by anyone. It simply exists, passed from the future to the past in an endless, closed loop. It has no true origin or author. This is the bootstrap paradox, named for the absurd idea of pulling yourself up by your own bootstraps. Information or an object is caught in a causal circle, becoming its own cause. The classic example is giving William Shakespeare a complete copy of his own plays before he writes them. He then simply publishes them as his own work. The plays were not written by Shakespeare, they were given to him by a time traveler. But that traveler only had them because Shakespeare published them. So where did the language, the poetry, the characters first come from? They came from nowhere. They always were. This paradox strips away the comfort of linear history. It suggests that certain things in our world might not have a starting point. Perhaps a groundbreaking invention, a mathematical formula, or even a cultural myth in our own timeline was not invented or discovered, but bootstrapped into existence from a future that itself depends on that very thing. It forces us to ask a profound philosophical question: can something exist without ever having been created? In a universe that allows closed time-like curves, the answer might be yes. Reality could contain elements that are literally timeless, self-created artifacts spinning in the loom of causality. The bootstrap paradox does not create a logical contradiction like the grandfather paradox, but it creates a deep mystery of origin. It reveals a universe where not everything needs a first cause, where some ideas might just be, forever echoing between the future and the past. A predestination loop is a trap set by time itself. Where the bootstrap paradox creates information from nothing, the predestination paradox ensures that events are set in stone, often by the very person trying to change them. This is the universe's most cruel and elegant form of irony. Imagine a historian learns of a terrible fire that destroyed a priceless museum wing in 1922. Determined to save history, she builds a time machine and travels back to the night of the blaze. Her plan is simple: arrive early, find the cause, and stop it. She materializes in a dark storage room, her time machine disguised as an electrical panel. In her haste, she knocks over her bag. A lantern inside shatters and the fuel spills across the floor. She fumbles for a light switch and the old wiring sparks. In an instant, flames erupt from the very spot she arrived. She realizes with dawning horror that there was no original cause. She is the cause. Her attempt to prevent the disaster was the very action that created it. The fire was always started by a time traveler from the future. This is a closed, self-fulfilling circle. Every detail of the event, from the spark to the specific pattern of the flames, was predestined by her own journey. Her free will was an illusion. Her choice to go back was the first link in a chain that loops back on itself. This paradox presents time as a story already written, where the characters believe they are making choices but are only reading their lines. The traveler does not change history, they fulfill it. Their knowledge of the future becomes the instrument that brings that future about. It is a loop with no escape because any attempt to break it only tightens the knot. This forces a haunting question. If you could see a terrible future, would your effort to stop it be the very thing that makes it happen? In such a universe, foreknowledge is not power but a prison sentence. The cruel loops of predestination show time as a prison, but what if the key to escaping into the future has been in our hands for over a century? This is not a theory, it is a proven fact of our universe. Albert Einstein's theories of special and general relativity tell us that time is not a universal constant ticking the same for everyone. It is a personal experience, a river that flows at different speeds depending on how fast you move or how deep a gravitational well you find yourself in. This is time dilation, and it is the only form of time travel we know for certain is real. Special relativity deals with speed. The faster you move through space, the slower your clock ticks relative to someone who is stationary. At everyday speeds, this effect is imperceptible, but approach the speed of light and time slows dramatically. General relativity adds gravity to the mix. The stronger the gravity, the slower time passes. A clock at sea level ticks very slightly slower than a clock on a mountaintop because it is deeper in Earth's gravitational field. We measure this with incredibly precise atomic clocks. This means that by simply moving fast enough or standing near a sufficiently massive object, you are traveling into the future relative to everyone else. The classic illustration is the twin paradox. Imagine two identical twins. One, an astronaut, boards a spacecraft capable of traveling at 90% the speed of light on a journey to a distant star and back. The other twin remains safely on Earth. From the Earth-bound twin's perspective, the journey might take, say, 20 years. He ages 20 years, but for the astronaut twin, due to the effects of relativistic speed, time on the ship passes much more slowly. When she returns, only 10 years have passed for her. She steps out of her ship to find her Earth-bound brother is now 10 years older than she is. She has effectively traveled 10 years into Earth's future. She cannot go back, but she has leaped ahead. This is a one-way ticket purchased with velocity. We see this happening on a smaller scale every day. The GPS satellites orbiting our planet experience time dilation from both their high speed and the weaker gravity in space. If their incredibly precise clocks were not constantly corrected for this relativistic effect, the entire system would drift by several miles each day, rendering navigation useless. So we are already practical time travelers, accounting for the warping of time just to get driving directions. This proven science opens a breathtaking possibility. A truly advanced civilization could use time dilation as a method of extreme future sight. A starship crew on a long journey at near light speed could return to Earth after what felt like a few decades for them, only to find that thousands of years had passed at home. They would be archaeological relics from humanity's past, stepping into a future they helped shape but never lived. Time dilation shows us that the future is not a fixed point we all arrive at together. It is a landscape, and we are all climbing its hills and valleys at different rates. The doorway to tomorrow is not a mysterious portal. It is the engine of a starship or the edge of a black hole. But while time dilation offers a one-way ticket to the future, what about a vehicle that could truly navigate the river of time? Enter the Alcubierre warp drive, a concept that sounds like pure science fiction but emerges from the hard mathematics of Einstein's field equations. Proposed by physicist Miguel Alcubierre in 1994, this engine would not propel a ship through space in the conventional sense. Instead, it would manipulate the fabric of space-time itself. The idea is to create a stable bubble of normal space around a spacecraft. In front of the bubble, space-time would be compressed, pulling the destination closer. Behind the bubble, space-time would be expanded, pushing the point of origin farther away. The ship inside this warp bubble would remain motionless relative to its local space, avoiding the crushing effects of acceleration and the relativistic speed limit. It would, in effect, ride a wave of distorted reality, moving faster than light from an outside perspective without breaking any local physics. This alone is revolutionary, but the deeper, lesser-known implication is its potential for time travel. Because the drive warps spacetime so severely, it creates conditions ripe for closed time-like curves. A ship using an Alcubierre drive on a specific, looped trajectory could, in theory, arrive back at its starting point before it ever left. From the perspective of the outside universe, the warp bubble's path through compressed and expanded spacetime could twist causality into a knot, allowing the ship to emerge into its own past. It is a side effect of manipulating the fundamental stage on which events play out. To build such an engine, however, we would need to command a substance that defies everyday intuition, exotic matter. This is not just rare or strange material, but matter with what physicists call negative energy density or negative mass. Unlike normal matter, which gravitationally attracts, exotic matter would repel. It would exhibit anti-gravity. This repulsive property is what the mathematics says is required to stabilize the warp bubble, to keep it from collapsing and to create the expansion of spacetime behind the ship. We have glimpsed hints of such effects in lab experiments with quantum fields, like the Casimir effect, where negative energy densities appear between two closely spaced metal plates. But the amounts needed for an Alcubierre drive are astronomical, far beyond anything we can currently conceive of producing. The Alcubierre drive remains a dazzling blueprint on a chalkboard, a testament to the fact that the laws of physics, as we understand them, do not explicitly forbid bending the universe to our will. It transforms time travel from a passive trick of gravity or speed into an active feat of cosmic engineering, suggesting that a sufficiently advanced civilization might not just find time machines, but build them from the twisted fabric of reality itself. The fabric of reality grows even stranger when we peer into the quantum realm. Here, particles can be linked across vast distances through a phenomenon called entanglement, a connection so profound it seems to defy space itself. Two entangled particles, even if separated by the width of a galaxy, remain mysteriously bound. Measure the spin of one, and the other instantly assumes a corresponding spin, as if they share a single existence. This spooky action at a distance, as Einstein called it, appears to happen faster than light, raising a tantalizing and controversial question. Could this connection also defy the flow of time? Some interpretations of quantum mechanics suggest that entangled particles might not just be communicating across space, but backwards through time as well. This idea, known as retrocausality, proposes that effects can sometimes precede their causes on the quantum scale. The evidence is not in a time machine, but in the bizarre results of certain laboratory experiments. One of the most famous is the delayed choice quantum eraser. In this setup, scientists can seemingly decide, after a particle has already been detected and its path recorded, whether that particle traveled as a wave or a particle. By erasing information about its path after the fact, they can change the historical outcome recorded moments before. From a classical perspective, this looks like the present reaching back and rewriting the past. Of course, most physicists interpret this not as literal time travel, but as a demonstration that quantum systems do not have definite properties until they are measured. The past is not being changed, it is being created by the present act of observation. Yet, the retrocausal interpretation is a compelling minority view. It suggests that when we measure one entangled particle, our action sends a signal backwards in time to the moment of entanglement, forcing its partner into a corresponding state. In this view, the future is whispering to the past, guiding it into shape. This turns causality on its head, painting a universe where the rigid arrow of time is softened at the quantum level, replaced by a web of two-way influence. If true, it means the bedrock of our experience, that cause always comes before effect, is merely a statistical average of a much weirder, more fluid reality. The implications are dizzying. Could our choices in the present be subtly shaped by potential futures? Are entangled particles not linked across space but across time, acting as a single entity stretched through the fourth dimension? While far from proven, these quantum mysteries remind us that time, as we feel it pass, may be the grandest illusion of all. Stephen Hawking looked at these dizzying possibilities and proposed a cosmic safety mechanism. His chronology protection conjecture is a bold and elegant idea. The laws of physics contain a built-in failsafe that prevents time travel to the past, thereby protecting the sequence of cause and effect from paradox. Hawking famously argued that if time travel were possible, we should see tourists from the future. Since we do not, he quipped, it is strong evidence that it simply cannot happen. But his conjecture goes beyond a simple observation. It suggests a specific physical process that would automatically sabotage any attempt to create a closed time-like curve. The proposed mechanism involves the strange behavior of the quantum vacuum. Even in empty space at the tiniest scales, particles and antiparticles are constantly flickering into and out of existence. These are quantum fluctuations, borrowing energy from nothing for an immeasurably short time. Normally, these fluctuations cancel each other out, but Hawking and others calculated that near the throat of a nascent wormhole time machine, or in the twisted spacetime of a forming time loop, these fluctuations would not cancel. Instead, they would be amplified. Virtual particles could get caught on the time loop, traveling around and around, hitting their own tails. With each pass, their energy would add up, creating a runaway feedback loop. The energy density would skyrocket towards infinity, creating a devastating blast of radiation or causing the space-time structure itself to collapse. In essence, the act of trying to stitch time into a loop would summon a firestorm from the quantum void that destroys the loop before it can be used. It is nature's ultimate paradox police, a law of cosmic self-preservation. This is not a prohibition written in some rulebook, but an emergent property of physics. The universe, according to this view, is wired to keep history linear and sensible. Any attempt to twist time into a knot triggers a catastrophic fail-safe, like a circuit breaker tripping to prevent a fire. Hawking's idea offers a comforting resolution to the frightening implications of paradoxes. It suggests reality has a kind of immune system against causal chaos, ensuring that yesterday stays yesterday. Yet it remains a conjecture, a brilliant argument rather than a proven law. It tells us that if we ever hear the engine of a time machine whirring to life, we might also hear the universe preparing to blow a fuse. The philosophical weight of this paradox is immense. It forces us to confront the very nature of existence. What does it mean for something to be real if it was never created? In a normal, linear timeline, everything has a cause. A tree grows from a seed, a book is written by an author, a symphony is composed by a musician. This chain of causality is the backbone of how we understand reality. The bootstrap paradox or ontological paradox snaps that chain. It presents us with logical entities that are self-existing, timeless loops in the fabric of causation. The object or information simply is forever circulating with no creator and no first moment. This challenges one of our most fundamental assumptions, that to exist something must have begun. Perhaps within the twisted geometry of closed time-like curves, our linear logic simply breaks down. In those loops, existence does not require an origin story. A thing can be its own reason for being. This leads to a haunting question about our own universe. Could anything around us right now be such a loop? Is it possible that a famous invention, a piece of classic art, or even a foundational scientific principle in our history has no true point of conception? That it was always just there, passed hand to hand from a future that itself depends on it. The paradox suggests a universe where not all things are made, some are found endlessly in the attic of time. This idea leans heavily toward a deterministic cosmos. If the music always goes back to the composer, then every action within the loop is fixed. The time traveler has no free will in the matter. They are compelled to complete the circle, to deliver the object that will inspire their own journey. It paints time as a perfect, self-consistent mechanism where every gear, including our choices, is already meshed. Yet there is another, more liberating interpretation. Perhaps these loops are not prisons, but a new form of creation. In a universe with time travel, causation becomes a web, not a line. An object bootstrapped into existence is no less real than one built in a factory. Its reality is defined not by a point of origin, but by its persistent presence in the causal web. It exists because it consistently affects the world. In this view, the paradox does not break logic. It simply expands our definition of what it means to come into being. The ultimate lesson of the ontological paradox is humility. It reminds us that our instinct for linear, simple stories of creation might be a limitation. The universe, if it allows these loops, operates on a logic far older and more intricate than our own, where something can indeed come from nothing, as long as that nothing is a closed loop in time. Even a simple billiard ball can create a temporal crisis. Physicist Joseph Polchinski crafted a beautifully elegant thought experiment that strips away human drama and reduces the paradox to pure physics. Imagine a wormhole time machine, its two mouths separated in time. The future mouth opens just a moment before the past mouth. Now take a billiard ball and roll it toward the future mouth at a perfect, gentle angle. The ball enters, travels through the wormhole, and emerges from the past mouth a split second before it began its journey. It now exists in the same space as its younger self, still rolling toward the entrance. The potential for a paradox is immediate and mechanical. If the older ball emerges on a collision course, it could strike its younger version, knocking it off its path. If the younger ball is deflected, it never enters the wormhole. But if it never enters, then the older ball that just emerged to cause the collision could never have existed. It is the grandfather paradox played out with spheres and momentum instead of people and pistols. So what does the universe do? The intuitive, linear answer is a catastrophic contradiction. But Polchinski and his colleagues calculated that the laws of physics demand a consistent solution. They found one, and it is a thing of dynamical beauty. The ball from the future does not emerge to deliver a knockout blow. Instead, it emerges on a path that delivers a perfectly calculated, glancing impact. This subtle nudge alters the younger ball's trajectory just enough. A tiny change in angle, a minuscule shift in speed so that it still enters the wormhole, but now on the exact path required to become the older ball that delivered the nudge. The collision is not a prevention, it is an essential part of the loop. The younger ball enters because it was hit, and it emerges to hit itself so that it will enter. Every action is both cause and effect, locked in a stable, self-consistent cycle. This solution is powerful because it is purely physical, governed by the deterministic laws of motion. It shows that within the bizarre geometry of closed time-like curves, the universe does not allow paradoxes to happen. Instead, it finds the one stable, non-contradictory arrangement of events, no matter how unlikely it seems from the outside. The balls find the only dance where every step leads inevitably to the next, creating a loop that has always existed. This thought experiment transforms paradox from a logical error into an engineering puzzle. It suggests that if time loops are possible, they would not be scenes of chaotic contradiction, but of perfect, almost predetermined dynamical balance. The universe, it seems, would rather choreograph an impossibly precise game of cosmic pool than allow a single ball to vanish from the table. The billiard balls find their perfect, paradoxical dance because the stage itself may already be complete. This brings us to a theory that reshapes our entire conception of reality, the block universe. Imagine all of time and space not as a flowing river, but as a vast, four-dimensional loaf of bread. The three spatial dimensions, length, width, and height, form the slice. The fourth dimension, time, is the entire loaf from crust to crust. In this model, the past, the present, and the future are not successive states. They all exist simultaneously, eternally, and equally fixed within the block. Your birth, your life, and your death are all out there, just as real and permanent as the cities of Paris and Tokyo are real and permanent in space. From this God's eye view, there is no special now moving forward. What we experience as the flow of time is just our consciousness moving along our personal world line, like a tiny ant crawling along a single thread woven through the immense fabric of the block. We perceive one moment at a time in sequence, but the entire sequence is already laid out. This idea, also called eternalism, comes directly from Einstein's own thinking. After the death of his friend Michel Besso, he wrote a letter of condolence that contained a profound insight. He said, "People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." In the block universe, the distinction truly is an illusion of perspective. So what does this mean for time travel? It transforms the concept completely. Traveling to the past or future is no longer about changing history, because history is not a story being written. It is a sculpture already finished. Time travel becomes mere navigation through a static dimension, like traveling north instead of south. You are not rewriting the book, you are simply turning to a different page that has always been there. This perspective dissolves many paradoxes into simple errors of navigation. The grandfather paradox, in the block, it is an impossibility, like trying to draw a square circle. The geometry of the block does not contain a world line where you are born from a grandfather you killed. Your world line is a single, unbroken thread. If you appear in the past, that appearance was always a part of the block's structure. Your actions there were always a feature of that moment, woven into the immutable whole. You were always part of your grandfather's history. The bootstrap paradox also loses its mystery. The symphony with no origin. In the block, it simply has a world line that forms a closed loop within the larger structure. It does not need a creator because from the four-dimensional perspective, it is just a peculiar, self-connected shape. It exists as surely as a circle exists with no starting point. This view is both liberating and deeply unsettling. It offers a universe free from causal chaos, where every paradox is smoothed into a predetermined shape. But it also suggests a cosmos without free will in the traditional sense. Our choices feel real, but in the block, they are like the grooves on a record, fixed, permanent, and simply being played. We are the music, not the composer. The block universe theory does not tell us how to build a time machine, but it redefines what a time machine would even do. It would not be a vehicle for change, but a device for shifting your point of view within an eternal, unchanging tapestry where every moment, from the Big Bang to the heat death of everything, is forever real. The block universe feels frozen and predetermined, but quantum mechanics insists on a world of chance and possibility. David Deutsch, a pioneer in quantum computing, found a brilliant way to bridge this gap, applying the raw power of quantum theory directly to the heart of time travel paradoxes. His work begins with a profound shift in perspective. Instead of imagining a single time traveler going back to a single past, Deutsch asks us to consider a quantum time traveler, a traveler who exists in a superposition of states. In the quantum realm, a particle can be in multiple places or have multiple properties at once until it is observed. Deutsch applies this logic to a person stepping into a time machine. In his model, the traveler does not go to one specific past. They enter a superposition, interacting with all possible versions of the past simultaneously across the infinite branches of the multiverse. To solve a paradox like the grandfather scenario, Deutsch constructs a quantum computational circuit. Imagine a qubit, the basic unit of quantum information, representing the time traveler's decision to interact with their grandfather. In a classical setup, this leads to contradiction. But in Deutsch's quantum circuit, the qubit is put into a superposition of both interacting and not interacting. The computation runs in a closed loop, with the output from the future feeding back as the input to the past. Through the mathematics of quantum interference, the only stable, consistent solutions that emerge are those where the probabilities cancel out the paradoxical outcomes. The traveler might emerge from the machine having both caused and not caused an event, but when the quantum wave function collapses, they find themselves in a branch of the multiverse where their actions were logically consistent. They did not erase themselves, they simply ended up in a universe where their journey's outcome fits without contradiction. This is not time travel as a dramatic rewriting of history, but as a subtle, probabilistic navigation through the multiverse. The paradox is not avoided, it is processed. Every possible interaction plays out across countless worlds, and the traveler's consciousness follows one self-consistent path. Deutsch's model provides a breathtakingly elegant answer. It tells us that if time travel is ever possible, it will not be a classical journey. It will be a quantum one where every choice spawns new realities, and every traveler is less a historical vandal and more a participant in an infinite, consistent symphony of cause and effect across all of creation. Deutsch's quantum traveler navigates a sea of possibilities, but one cosmic object promises a more direct, if terrifying, passage. At the heart of a rotating black hole lies not a point of infinite density, but a gateway shaped like a ring. This is the ring singularity of a Kerr black hole, a theoretical structure that redefines our understanding of these gravitational monsters. Unlike the classic Schwarzschild black hole, which possesses a zero-dimensional point singularity, a place where gravity becomes infinite and spacetime curves to a breaking point, a Kerr black hole spins. And this rotation changes everything. The immense centrifugal force from the spin stretches the singularity from a point into a ring, a one-dimensional loop floating in the plane of the black hole's rotation. This ring is not a solid object you could touch, but a boundary where our laws of physics fail, a tear in the fabric of reality itself. The mathematics describing this ring suggest it is a place of naked singularity, potentially exposed beyond the event horizon. But more intriguing than its shape is what might lie on the other side. The equations indicate that the very center of this ring is not a wall of infinite gravity, but a portal. It is theorized that passing through the center of the ring singularity, a feat of unimaginable precision and survival, could allow an object to avoid the crushing fate of the central point. Instead of being spaghettified and destroyed at a zero-dimensional dot, a traveler might emerge into a completely different region of spacetime. This region could be another part of our own universe, a separate universe entirely, or even a different time. The ring acts not as an end, but as a throat, a connection to somewhere else. It becomes a natural, albeit violent, wormhole built by the cosmos. The contrast with a non-rotating black hole is stark. A Schwarzschild black hole is a dead end. Its event horizon is a one-way membrane, and its point singularity is a cosmic trash compactor from which no information ever returns. It is a pit with no exit, but a Kerr black hole with its ring and the complex geometry of its inner horizons presents a labyrinth. Some paths within it could theoretically lead to closed time-like curves, loops in time that circle the ring. This makes it not just a gateway through space, but a potential machine for navigating time. Of course, the practical barriers are absolute and horrifying. To even approach the ring, you must survive crossing the inner event horizon, a region of intense, chaotic radiation. You must navigate tides of gravity that would pull your head and feet in opposite directions with unimaginable force. And you must hit the exact center of a spinning ring of oblivion, a target smaller than an atom while moving at relativistic speeds. It is less an engineering challenge and more a suicidal fantasy. Yet, as a pure concept, the ring singularity transforms the black hole from a tomb into a crossroads. It suggests that the universe's most destructive phenomena might also be its most profound architects, weaving tunnels through the bulk of reality with nothing but spin and gravity. If such structures exist, they are the ultimate natural time machines, forged in the collapse of massive stars waiting in the darkness. The ring singularity is a gateway built by gravity, but there are particles that might bypass gravity entirely. Tachyons are a purely hypothetical class of particles with one extraordinary property: they always travel faster than light. According to the theory of special relativity, nothing with mass can be accelerated to the speed of light. It would require infinite energy. Tachyons, however, are theorized to be born already moving faster than light, and they cannot slow down to or below light speed. They exist, mathematically at least, on the other side of the light-speed barrier. Their name comes from the Greek word for swift, and if they were real, they would redefine the cosmic speed limit. But their strangest implication is not about speed, it is about time. Due to the relativistic effects of moving faster than light, a tachyon's internal clock, from our perspective, would appear to run backwards. For a tachyon, the journey from point A to point B might feel normal, but to us watching, its cause and effect would be reversed. It would arrive at its destination before it left its source. This leads to the concept of the tachyonic antitelephone, a thought experiment where these particles could be used to send signals into the past. Imagine you and a friend have a pair of devices that can generate, detect, and interpret tachyons. You agree on a simple code: a burst of tachyons means yes, no burst means no. Your friend is on a distant planet 10 light-years away. You decide to ask a question. You send a tachyon message that, because it travels faster than light, arrives almost instantly from your friend's point of view. Your friend receives your question and immediately sends a tachyon reply. Now, because the reply is also faster than light, the relativistic math shows it could arrive back at your location before you even sent your original question. You could receive an answer to a question you have not yet asked. This creates a closed loop of information, a communication-based grandfather paradox. You could, in theory, send a message to your own past self saying, "Do not send the message." The logical contradiction is immediate and profound. For this reason, most physicists are deeply skeptical. While the equations of special relativity do not explicitly forbid particles that always travel faster than light, they create immense problems for causality. The prevailing view is that if tachyons exist, they are likely either undetectable ghosts that cannot interact with normal matter in any coherent way, or their existence is mathematically possible but physically forbidden by a deeper law that protects causality. Using them for communication seems to violate the fundamental principle that cause must precede effect, creating paradoxes that the universe appears to avoid at all costs. The tachyonic antitelephone remains a fascinating footnote, a reminder that the ultimate speed limit of light may be less about velocity and more about preserving the very sequence of time itself. The mathematics of rotating matter can weave time itself into knots. Long before Tipler's cylinder, another physicist, Willem van Stockum, found a simpler, more elegant path to the past. In 1937, he solved Einstein's equations for a very specific scenario: an infinitely long, perfectly straight cylinder made of dust, all spinning in unison. Dust in this context is a cloud of non-interacting particles, a simplified model of matter. Van Stockum was not trying to build a time machine, he was exploring the pure geometry of general relativity. His solution revealed something astonishing. The rotation of this dust cylinder drags spacetime around it so severely that, beyond a certain critical radius, closed time-like curves appear. A traveler circling the cylinder in the right orbit could loop back to their own past. This was one of the very first exact solutions to show that time travel was not just a philosophical idea, but a mathematical possibility hidden within Einstein's own work. It proved that rotation alone, given enough scale, could twist causality into a circle. Yet, like Tipler's later work, it relied on an infinite cylinder, a physical impossibility. It was a ghost in the machine of physics, a proof of concept that the universe's rulebook contained the instructions for a temporal loop. But what if the loop was not in a machine, but in the cosmos itself? This is where one of the greatest minds of the 20th century, Kurt Gödel, entered the stage. Famous for his incompleteness theorems in logic, Gödel turned his genius to general relativity and in 1949 delivered a cosmological shock. He found a solution describing a universe that is not expanding, not static, but slowly rotating as a whole. In Gödel's universe, every galaxy, every star, every particle is part of a grand cosmic whirl. The implications for time are profound. In such a rotating cosmos, the fabric of space-time is dragged along with the motion. This universal frame dragging creates closed time-like curves on a cosmological scale. You would not need a black hole or a cylinder. You could simply get in a sufficiently powerful rocket ship and fly a large enough circle through the galaxies. If you traveled far enough on the right path, you would eventually return to your own starting point in space and also to a moment in your own past. Time travel would be a natural feature of the environment, like wind or gravity. You could visit any event in history, provided you had the fuel and the patience for the journey. Gödel's universe was a direct challenge to our understanding of cause and effect. In a cosmos where you can literally meet your younger self, the idea of a fixed, linear past evaporates. There is no universal, now, no objective flow of time. What we perceive as the arrow of time becomes a local artifact, a product of our limited perspective within a much stranger, looping reality. Einstein was deeply troubled by his friend's discovery. It showed that his own equations, the very foundation of modern physics, permitted universes where time was not a river flowing in one direction, but a Möbius strip with no beginning or end. Gödel had used relativity not to explain the universe we see, but to reveal all the universes we could possibly see, including ones where history is an open book you can revisit. While our own universe shows no evidence of such overall rotation, Gödel's model stands as a permanent monument to a terrifying and beautiful truth. The laws of physics do not guarantee our familiar, sensible timeline. They allow for worlds where time is a labyrinth and every moment is just a turn away from any other. Gödel's rotating universe dissolves the past into a labyrinth, but here on Earth we face a simpler yet deeper divide. Two rival visions of time have shaped every story and every theory. Is history an unchangeable monument or wet clay waiting for our hands? This is the great schism between the immutable past and the mutable timeline. In the fixed timeline model, the past is a locked door. You can visit it, but you cannot alter it. Any attempt to change history was always part of history. Your actions back in time are not corrections, they are fulfillments. You were always there. This is the realm of the Novikov self-consistency principle and the predestination paradox. The universe operates like a masterfully edited film. Every scene, including the time traveler's cameo, is already in the final cut. The fire you tried to prevent was always started by you. The book you gave your younger self was always written by no one. This model offers a clean, paradox-free cosmos, but it comes at the cost of free will. It suggests a deterministic block universe where our journey through time is just us reading a script we helped write millennia ago. The mutable timeline model offers freedom, but at a terrifying price. Here, the past is malleable. Step on a butterfly in the Cretaceous, and you might return to a world where humans never evolved. This is the universe of branching realities, where every change forks the timeline, creating a new future that overwrites the old one or exists alongside it in a parallel branch. It is the realm of dramatic consequence, where heroes race to fix alterations and villains seek to reshape the world in their image. This model feels intuitive to our sense of agency. Our choices matter even across centuries, but it introduces the chaos of paradox and the existential dread of erasure. If you change the past, what happens to the future you left behind? Does it vanish, or do you simply strand yourself in a new branch? So which vision does physics favor? Our current understanding, surprisingly, leans toward the immutable. General relativity, with its solutions for closed time-like curves, inherently describes a fixed four-dimensional spacetime geometry, a block universe. The mathematics of these curves demand self-consistency. They cannot contain contradictions. This aligns perfectly with the fixed timeline. Quantum mechanics, with its many worlds interpretation, offers a mutable multiverse, but here changes do not alter your original past. They spawn new ones. From the perspective of a single timeline, however, physics appears to have a strong preference for consistency over change. The universe seems to be a story where every word, even the unexpected ones from a time traveler, was always part of the manuscript. The mutable timeline, while thrilling, may be a narrative device that clashes with the universe's apparent need for causal harmony. Yet the debate remains open, a fundamental tension between our desire for freedom and the cosmos's potential preference for a single, immutable truth. The universe may already be woven with threads that connect moments across time. Quantum teleportation, a real and demonstrated process, offers a glimpse of a mechanism far stranger than any wormhole. It does not teleport matter, but information, the exact quantum state of a particle. Here is how it works in the present. You have two entangled particles, call them A and B. You keep particle B and send particle A to a distant location. Now you have a third particle, C, with a quantum state you want to teleport. You perform a special joint measurement on particle A and particle C at your location. This measurement destroys both A and C, but it instantly forces particle B, no matter how far away, to take on the exact quantum state that C originally had. The information about C's state has been teleported across space using the entanglement link as a channel. Now, stretch this concept across time instead of space. For time travel via quantum teleportation, you would need to create an entangled pair of particles and then separate them not just in distance but in time. One particle would need to be sent or preserved into the past while its partner remains in the future. This creates a quantum link that bridges different moments. If you could achieve this, you could, in theory, perform the teleportation measurement in the future on a target object and its entangled partner, destroying the original in the process. The complete quantum blueprint of that object would then be instantaneously reconstructed onto the particle waiting in the past. It would be less like flying a ship through a tunnel and more like sending a flawless, state-by-state facts of yourself to a receiver in an earlier era, with the original you dissolving into noise. The person who steps out of the receiver in the past would have every memory, every atom arranged identically. They would be you in every meaningful sense, just reassembled from local matter and energy at the destination. The philosophical implications are dizzying. Is this travel, or is it copying and suicide? The original you is obliterated in the teleportation process. From your perspective in the future, you step into the machine and cease to exist. Your consciousness does not make the journey. A perfect replica awakens in the past, convinced it just arrived. This touches on the classic transporter paradox from science fiction. If your body and mind are perfectly recreated elsewhere, is that still you? For time travel, the paradox deepens because this new you now exists in a timeline that leads back to the moment you were just destroyed. The technical hurdles are, of course, beyond monumental. First, you must create that temporal entanglement link. How do you send one half of a pair into the past to begin with? You would need another time travel method just to set up the apparatus. Second, quantum teleportation requires sending classical information, the results of the joint measurement through normal channels to complete the process. To teleport to the past, you would need to send that data backwards in time as well, perhaps via a second channel. Finally, the scale is incomprehensible. Teleporting the quantum state of a single photon is a Nobel Prize-winning feat. Teleporting the near-infinite quantum complexity of a human being, with every neuron and memory intact, is a challenge that may forever remain in the realm of speculation. Yet, as a thought experiment, it reframes time travel not as movement but as transmission. It suggests that if the universe's quantum web can stitch space together, perhaps with enough manipulation, it could also stitch together different nows, allowing the essence of a thing to leap across the ages in a flash of entangled light. This interpretation of many worlds offers a profound and lonely form of time travel. The moment you act to change a past event, you are not rewriting history. You are cutting the cord. Your original timeline, the one that produced you and sent you back, continues on perfectly intact, completely unaffected by your actions. But you are no longer part of it. You have now become a permanent fixture in a brand new branch of reality, one that diverged the instant your boot touched ancient soil or your voice warned a king. This is a one-way ticket with no return address. The future you knew, the people you loved, the home you left behind. They are all still there, but they are now separated from you by an impassable gulf of branching probability. You can never go back to them. In this new branch, the consequences of your actions unfold. You might prevent a tragedy, inspire a revolution, or simply leave a cryptic message carved in stone. This new world evolves with your intervention woven into its fabric. You might live out your days hailed as a prophet or hunted as a demon, but you will live them in a universe that is, in a very real sense, an orphan. Its history now includes you, but it has no prior connection to the chain of events that created you. This raises a haunting emotional question. If you travel back to save a loved one from an accident and succeed, have you truly saved them? The person you rescue is not the one you lost. They are a perfect duplicate, living in a new world where the accident never happened. The version you mourned is still gone forever in the timeline you can never return to. Your act is one of creation, not restoration. You have not healed your old wound. You have started a new story in a different book, leaving the old one with its pain still on the shelf. This theory transforms the time traveler from a hero into a kind of cosmic refugee. Their journey is not about fixing their own past, but about abandoning it to build something new elsewhere. Every decision becomes monumentally consequential, not because it changes what was, but because it irrevocably defines what will be for the branch you now call home. There is no safety net of paradox, no cosmic undo button. Once you step off your original thread, you are falling forever through the infinite tapestry of the multiverse, weaving your own new thread as you go. The ultimate price of changing history may be the permanent loss of everything you ever called your own. Perhaps the most intimate form of time travel requires no machine at all. It unfolds within the theater of the mind. Theory 24 explores the pseudo-time machine, the idea that consciousness alone might slip the bonds of the present. This is not about moving atoms through a wormhole, but about information, memory, or awareness somehow leaping across the timeline. It lives in the hazy borderland between philosophy, mysticism, and the unexplained quirks of human perception. Consider the work of John C. Lilly, a physician and neuroscientist who ventured far beyond conventional science. In the mid-20th century, Lilly became famous for his research on dolphin communication and his pioneering, controversial use of sensory deprivation tanks. Floating in silent darkness, cut off from external stimuli, Lilly reported experiencing profound alterations in consciousness. He described encountering what he called meta-programs, vast networks of information that seemed to exist outside of linear time. In these states, he felt he could access memories that were not his own, or perceive events from different historical periods as if he were there. Lilly believed the brain was a receiver, and under the right conditions, it could tune into signals from other times. While his methods were far from rigorous science, his experiences point to a deep human intuition that our awareness might not be as firmly anchored to the now as we think. This intuition fuels ancient concepts like astral projection through time, the idea that a non-physical essence of a person could journey across the ages, observing but not interacting. Why does this idea persist? It offers a seductive explanation for those eerie glitches in our daily experience. That overwhelming sense of déjà vu, the feeling you have lived this exact moment before, could be framed as a brief, accidental overlap with a past or parallel consciousness. Vivid precognitive dreams, where you dream an event in startling detail only to see it unfold days later, feel like fragments of a future memory leaking backward into your sleeping mind. These phenomena are notoriously difficult to study, often dismissed as coincidence or the brain's pattern making machinery misfiring, yet their subjective power is undeniable. They make time feel fluid, personal, and strangely porous. The appeal of consciousness-based time travel is deeply philosophical. It sidesteps all the physical paradoxes of moving a body. Information has no mass. It does not disrupt the past by its mere presence. If only a non-interactive awareness travels, it creates no grandfather paradox because it cannot lift a finger to change a thing. It turns time travel into a purely observational act, like watching a historical film you cannot pause or alter. This theory resonates because it mirrors how we already experience time in our own mind. We constantly travel mentally, through memory to the past and through imagination to the future. The pseudo-time machine simply asks, what if that travel could become literal? What if the mind's eye could focus on a real moment in history, not just a reconstruction? While it offers no equations or blueprints, it speaks to a profound hope that the essence of who we are might be free to explore the vast library of time, unshackled from the frail vessel of the body, witnessing the tapestry of reality from within. But the mind's journey is a ghost compared to the brutal engineering demands of a real machine. To hold open a gateway through space and time, you need a material that defies the ordinary rules of the universe. This is the monumental hurdle of negative mass and negative energy. For a wormhole to be stable and safe enough to walk through, or for an Alcubierre warp bubble to hold its shape, the equations of general relativity demand something extraordinary. They require a form of matter that possesses what physicists call negative energy density. Imagine gravity as a one-way force that always pulls things together. Normal matter, like the atoms that make up a planet or a person, creates positive curvature in space-time, a gravitational well that attracts. Exotic matter with negative energy density would do the opposite. It would create a kind of anti-gravity, a repulsive force that pushes space-time apart. This repulsion is the key. In a wormhole, the immense gravitational pull of the positive mass trying to collapse the tunnel must be counteracted. You need this exotic matter to line the throat, propping it open like a scaffold against the crushing weight of the universe. Without it, the wormhole would snap shut faster than light could pass through, making it useless for travel. Similarly, for a warp drive, you need negative energy to expand spacetime behind the ship and compress it in front, creating the wave to ride. So does such a substance exist? We have never held a chunk of negative mass in our hands, but quantum mechanics offers a tantalizing hint. In the bizarre realm of the very small, empty space is not truly empty. It seethes with virtual particles, pairs of particles and antiparticles that flicker into and out of existence, borrowing energy from the vacuum for an immeasurably brief moment. Under certain conditions, this quantum foam can be manipulated to produce a measurable negative pressure. This is demonstrated in a real laboratory phenomenon called the Casimir effect. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, only a few nanometers apart. The gap between the plates is so tiny that only certain wavelengths of virtual particles can flicker into existence there. Outside the plates, a wider variety of wavelengths can appear. This imbalance creates a net pressure that pushes the plates together. From the perspective of the space between the plates, this is equivalent to a region of negative energy density. The vacuum between them has less energy than the vacuum outside. It is a minuscule effect, but it is real, and it proves that negative energy densities are not pure fantasy. They are a permitted feature of our quantum universe. The problem is one of staggering scale. The amount of negative energy needed to stabilize a wormhole large enough for a person is astronomical. Some calculations suggest it would require the equivalent negative mass of an entire star or more, concentrated in a precise configuration. The Casimir effect produces a whisper of this force. We would need a cosmic shout. Furthermore, there are deep theoretical concerns. Large concentrations of exotic matter might violate fundamental physical principles, like the average null energy condition, which essentially says that negative energy cannot dominate over positive energy for too long or on too large a scale. The universe might allow for these strange materials in fleeting, microscopic doses, but forbid us from gathering enough to build an archway through time. This requirement transforms time travel from a question of geometry into a question of material science. It tells us that even if we master the math of warping space-time, we are left searching for a phantom material, a kind of cosmic anti-gravity cement, to make the dream a reality. The bridge to yesterday may be designed, but we are still searching for the stones to build it. Even the phantom of exotic matter cannot answer a simple, haunting question. If time travel to the past is possible, where is everybody? This is the Fermi paradox of temporal physics, named for the physicist Enrico Fermi, who famously asked about extraterrestrial life. Where are they? We can ask the same of our descendants. A future with time machines, even just one, would likely see an explosion of temporal tourism, research, and perhaps even colonization. The past should be swarming with visitors from tomorrow. Yet our history books, our archaeological digs, and our daily lives show no definitive evidence. Not a single selfie with a dinosaur, no anachronistic technology in ancient ruins, no future historian correcting our records. This profound silence is one of the strongest common sense arguments that backward time travel may simply be impossible. Perhaps the universe's laws, through mechanisms like Hawking's chronology protection, actively prevent it. The eerie emptiness of the past suggests we are alone in time, prisoners of the present moment, with no one from the future ever dropping in. But is that silence truly empty? Clever counter-arguments propose that the tourists might be here, just invisible to us. One possibility is the zoo hypothesis, adapted from the Fermi paradox. Perhaps a future civilization observes a strict non-interference policy. They treat the past as a sacred preserve, watching us from behind perfect camouflage, careful not to disturb a single event in their own history. Their technology would be so advanced, so seamlessly integrated into the background of reality, that we would never notice them. A time traveler's recording device might be the size of a dust mote, floating unseen through the ages. Their vehicles might phase slightly out of sync with our spacetime, making them ghosts in our peripheral vision, dismissed as tricks of the light. In this view, the past is not empty. It is a carefully managed exhibit, and we are the living diorama. Another compelling idea is that practical time travel might only work in one direction, forward. We already know this is possible through time dilation. A civilization could master relativistic travel, sending explorers on journeys that leap them millennia into the future, but they might never crack the puzzle of returning to an earlier point. The past could be a cliff you can only jump from, not climb back up, so the future might be full of time travelers from even further ahead, but none can visit us. We are the ancient, inaccessible past to them, a closed chapter they can read but never rewrite. Our timeline's quiet dignity is preserved simply because no one has the ticket to come back. The most elegant solution, however, comes from the branching multiverse. If every journey to the past spawns a new reality, then our specific timeline is pristine. No time traveler from our own future has ever visited us because the moment one tries, they branch off into a different world. In that new branch, their arrival is recorded and history is changed. But in our original branch, nothing happens. We continue on, untouched and unvisited, in a universe where time travel was never invented, or where every attempt to reach us simply created another parallel reality elsewhere. Our history feels lonely and linear precisely because we are on the trunk of a particular tree, and every time travel event is a leaf growing on a separate branch we can never see. The absence of tourists is not proof that time travel is impossible, but proof that our timeline is uniquely ours, a narrative thread that has never been intercepted. The quiet of the ages, then, is not a void but a signature of our own causal solitude. The silence of the past may be a clue written in the language of the universe itself. Our journey through these theories has revealed a fundamental split in reality's rulebook. General relativity, governing the vast cosmos of stars and black holes, paints time as a flexible dimension that can, in theory, be bent into loops and circles. Its equations are filled with doorways to yesterday, yet quantum mechanics, ruling the realm of the impossibly small, tells a different story. It suggests a universe built on probability and uncertainty, where the very concept of a smooth, bendable spacetime breaks down into a seething quantum foam. At this scale, the neat geometry of a closed time-like curve might dissolve into chaos, forbidden by the unpredictable jitter of reality's foundation. This is the great schism at the heart of modern physics, and it is why a working time machine remains a fantasy. We are missing the master key, a theory that reconciles these two titanic descriptions of reality. This is the quest for quantum gravity. Without it, our understanding of time is incomplete, like trying to read a novel with every other page ripped out. We can see the potential for loops in the large print of relativity, but the fine print of the quantum world might contain a clause that voids the entire contract. The problem is one of scale and substance. General relativity treats spacetime as a smooth, classical stage. Quantum mechanics reveals that stage is not smooth at all, but a turbulent sea of virtual particles and fluctuating energies. To know if a time loop is truly possible, we need to know how spacetime behaves when it is both massively warped, as near a black hole, and probed at the quantum level. Does the foam of quantum fluctuations rise up to fill and collapse any nascent wormhole, as Hawking's conjecture suggests, or can the loop hold firm, stitching itself together across the chaos? Our current theories are silent because they speak different languages. This is where the great unification efforts like string theory or loop quantum gravity enter the stage. They are attempts to write a single, consistent set of laws that work from the smallest particle to the largest galaxy. String theory, for instance, proposes that the fundamental ingredients of reality are not points but tiny, vibrating strings. The different vibrations correspond to different particles and forces. In this framework, the fabric of spacetime itself emerges from the collective behavior of these strings. The hope is that within such a theory, the question of time travel becomes calculable. We could, in principle, ask whether a specific configuration of strings and branes, the higher dimensional objects in string theory, allows for a stable, traversable closed time-like curve. The answer would not be a philosophical maybe, but a mathematical yes or no derived from first principles. It would tell us if the universe's ultimate building blocks permit the loops that relativity imagines. The pursuit of quantum gravity is not merely an academic exercise. It is a direct investigation into the architecture of causality. Unifying these theories would tell us if the flow of time is a fundamental current in the cosmos, or merely a compelling illusion that emerges from something deeper and stranger. Until that day, every design for a time machine is a sketch on a napkin, waiting for the final blueprint of reality to see if it can ever be built. the secret of time travel is locked in the space between the very large and the very small, waiting for a theory brave enough to bridge the gap. Physics may allow loops and reversals, but our minds tell a different story. We are all prisoners of a relentless one-way flow, a current that carries us from memory toward anticipation. This is the psychological arrow of time, and it is the most intimate barrier to time travel we possess. Why does yesterday feel fixed and solid, while tomorrow feels open and unknown? The answer may lie not in the stars, but in the very structure of our brains and the universe's deepest tendency toward disorder. The second law of thermodynamics states that entropy or disorder always increases in a closed system. A shattered glass does not reassemble itself. Smoke never flows back into a cigarette. This increase in entropy gives the physical universe a thermodynamic arrow of time, pointing from order to chaos. Our minds, it seems, are exquisitely tuned to this cosmic trend. We remember the past because it is a state of lower entropy, a more ordered arrangement of events that left a record in our neurons. We cannot remember the future because it is a state of higher entropy, a realm of branching possibilities not yet collapsed into a single, recordable fact. Our consciousness, moment by moment, is a process that feeds on this increasing disorder, organizing sensory input into a coherent narrative that only makes sense when played forward. Imagine watching a film reel in reverse. People rise from the ground, water flows uphill, and broken objects leap back together. Your brain instantly recognizes this as wrong because it violates the ingrained expectation of increasing entropy you have built from a lifetime of experience. A time traveler moving backwards through time would face this disorientation constantly. Their psychological arrow pointing forward would clash with a reversed physical arrow around them. Could the mind adapt? Perhaps, but it would be a profound and possibly terrifying rewiring. They would perceive cause and effect in reverse. They would see a shattered vase assemble itself from fragments before a hand placed it on a shelf. They would hear a conversation begin with farewells and end with greetings. Their own memories would be a fixed, unchangeable record of a future that, from their new perspective, had not yet happened. Would they feel they were moving toward that remembered future or away from it? The very concept of intention and action would unravel. If you drop a ball, you see it fall. In a reversed timeline, you would see it rise from the floor to your hand. To make it fall from your perspective, you would have to perform the action of catching it from below. Your will would be tied to effects that precede their causes, a cognitive nightmare. Some theorists suggest that consciousness itself might be inextricably linked to the thermodynamic arrow. To be aware is to process information, and processing information requires energy dissipation and an increase in entropy. In a region of space-time where entropy decreases, where order emerges from chaos, could a conscious mind even function? Or would it shut down like a computer trying to run a program written in a foreign code? A traveler caught in a closed time-like loop faces a different, equally bizarre psychological fate. With each cycle, they would experience the same events again and again. Would they retain memory from prior loops? If they do, the universe becomes a prison of déjà vu, where every choice feels futile because the outcome is predetermined by the loop's consistency. If they do not retain memory, then from their subjective view, each loop is a fresh first time, and the concept of being trapped is meaningless. They are simply living a life that, unbeknownst to them, repeats eternally. This forces a haunting question about our own reality. Are we on a linear path, or are we living one iteration of a loop we can never perceive? The psychological arrow of time is the final, personal frontier of this mystery. It tells us that even if we unlock the geometry of space-time, we must also unlock the architecture of our own awareness. To journey through time may require becoming a different kind of mind altogether, one that can perceive causality as a landscape to wander, not a river that carries it helplessly forward. The universe may have a firewall against paradoxes, and its name is cosmic censorship. This principle, proposed by physicist Roger Penrose, suggests a fundamental rule of reality. Singularities, those points of infinite density where the laws of physics break down, must be hidden from view. They must be clothed, veiled behind an event horizon, the ultimate point of no return of a black hole. The alternative is a naked singularity, a tear in the fabric of reality exposed to the wider universe. Such an object would be a window into lawlessness, where gravity becomes infinite and predictable cause and effect ceases to exist. Most physicists believe nature forbids this, that a cosmic censor always ensures an event horizon forms to shield the rest of creation from the unpredictable chaos at a singularity's heart. Now apply this logic to time travel. Closed time-like curves, the pathways to the past, are born from extreme warping of spacetime, the kind found at the brink of a singularity. What if cosmic censorship extends beyond simply hiding points of infinite density? What if its true purpose is to hide any configuration that would break causality? This theory proposes that the laws of physics actively censor time travel possibilities. They do not merely make it difficult, they place it permanently behind a one-way curtain. Any structure that could function as a time machine, whether it is the ring singularity of a Kerr black hole or the throat of a wormhole, is automatically shrouded by an event horizon. The gateway to yesterday exists, but it is locked inside a vault from which no information can ever escape to the outside universe. You could, in theory, enter the black hole and perhaps even encounter the time loop within. But you could never return to the external cosmos to report your findings or create a paradox in our shared timeline. The event horizon acts as the universe's ultimate editor, cutting the causal connection between the chaotic realm of time loops and the orderly, paradox-free reality we inhabit. It is a perfect solution. It allows the mathematics of general relativity to remain valid, permitting all those strange loops and curves in its solutions, while guaranteeing they never impact the observable universe. The past remains inviolate not because time travel is impossible, but because it is quarantined. Imagine finding a control panel for all of history, but it is locked inside a bank vault submerged at the bottom of the ocean. The treasure exists, but the environment surrounding it makes retrieval impossible. In this view, black holes are not just tombs for stars, they are prison cells for causality violations. The universe, it seems, would rather bury its most dangerous secrets behind impenetrable walls than risk them unraveling the chain of cause and effect that makes science and reality itself coherent. This idea offers a grim but elegant answer to the Fermi paradox of time travel. Where are all the tourists from the future? They are trapped. Any civilization that unlocks the secret and attempts to open a doorway to the past might succeed only in dooming itself to a causal prison, forever isolated inside the event horizon of its own creation, unable to ever signal the universe they left behind. The cosmic censor does not destroy time machines. It buries them alive, preserving the sanity of the cosmos by ensuring that whatever madness occurs behind the horizon stays behind the horizon. The cosmic censor buries paradoxes in black holes, but what if our entire reality is a program and time is just a variable in the code? This brings us to a theory that reframes every mystery through a digital lens. If our universe is a simulation, an immensely complex construct running on some unfathomable substrate of computation, then time travel is no longer about warping spacetime. It becomes a matter of data access and state management. In a simulation, the past is not a vanished moment, it is stored information. The future is not unwritten, it is either pre-rendered or being calculated in real time. Traveling to a previous point in history would be akin to loading an earlier save file or rewinding a recording to a specific frame. The traveler is not moving through a dimension, but having their conscious data stream reinserted into a prior state of the simulation's memory. From this perspective, the stubborn paradoxes that plague physics look like different kinds of software errors. The grandfather paradox is an attempt to execute an impossible command, like a program trying to delete its own source code. A well-designed system would not allow it. The simulation would likely have safeguards, administrative privileges that prevent users from making changes that crash the entire program. Your gun might jam, your will might falter, or the simulation could simply render your efforts futile, enforcing a form of digital Novikov self-consistency. The many worlds interpretation translates perfectly into this framework. Every choice point, every quantum event could trigger the creation of a new instance or a forked process. Changing the past does not alter the original timeline. It creates a new simulation branch, a separate server running a slightly different version of events. You are not erasing your home world, you are copying your character data into a new game file. The bootstrap paradox, where objects or information have no origin, is simply a glitch or a clever programming trick. It is data that exists outside the normal save structure, a fixed asset in the simulation's library that gets called into the runtime loop whenever needed, with no creation date in its metadata. The simulators themselves would have ultimate control over how paradoxes are handled. They could run regular backups of the entire universe state, allowing them to restore from a save point if a paradox threatens stability. They could implement a branching save system automatically, where every potential contradiction spawns a new reality instance, preserving the integrity of the original. Or, most simply, they could design the simulation's fundamental rules to make closed time-like curves and backward causation impossible from within the program. The laws of physics in this view are the source code, and if the code does not contain a function for move to past, then no entity inside the simulation can ever execute it. This digital framework even offers an answer to the eerie silence of the Fermi paradox for time. Where are all the tourists? If we are in a simulation, the administrators may have disabled the feature, restricted it to certain user levels, or placed our particular instance in a read-only mode for observational purposes. Our timeline feels linear and untouched because we are in a controlled environment, a historical simulation being run for study or entertainment where tampering is not permitted. The simulation hypothesis transforms the philosophical weight of time travel into a technical question. It asks not about the nature of time, but about the architecture of the reality engine. Are we in a deterministic program where every moment is pre-rendered and time travel is merely playback? Or are we in an interactive simulation where our choices matter and the system dynamically forks to accommodate them? This theory does not answer whether time travel is possible, but it redefines what possible even means. It suggests that the ultimate secrets of time may not be written in the fabric of space, but in the logic of the program that generates it, a code we are only beginning to glimpse through the lens of our own science. From the digital architecture of a simulated reality to the brutal censorship of black holes, our journey through these 30 mind-bending theories has taken us to the absolute frontier of human thought. We have wrestled with paradoxes that twist logic into knots, from the intimate dread of the grandfather paradox to the cosmic orphanhood of branching timelines. We have followed the mathematics of Einstein into rotating cylinders and Gödel's whirling universes, and peered into the quantum haze where particles whisper backwards through time. We have seen time as a block, eternal and unchanging, and as a river that can be warped by speed, gravity, or a ring of pure singularity. The sheer variety of ideas, from the hard physics of closed time-like curves to the wild speculation of consciousness projection, reveals one profound truth. The human drive to understand time is not just about building a machine. It is a fundamental quest to comprehend our place in the cosmos, to grasp the nature of cause and effect, memory and destiny. While a working time machine remains a fantasy locked behind impossible engineering and unresolved physics, the value of this exploration is immeasurable. Each theory, whether it ultimately proves true or not, is a stress test on the framework of reality. It stretches our imagination, challenges our intuition, and forces science to ask deeper, more daring questions. Contemplating these possibilities changes how we see our own timeline, lending a precious, fleeting weight to every moment we experience in this one-way flow. So we leave you with a final question and an invitation. Of all the theories we explored, which one reshaped your mind the most? Was it the chilling certainty of predestination loops, the lonely exile of the branching multiverse, or the elegant brutality of Hawking's chronology protection? Let us know in the comments below. Share your thoughts, your favorite theory, or your own wild speculation about the ultimate mystery of time. If this journey through the fabric of reality captivated you, please like this video and subscribe for more deep dives into the universe's greatest secrets. The conversation about time is far from over, and your perspective is a vital part of it. Thank you for exploring the impossible with us.